Hey guys, welcome back. So in this lesson we're going to visualize our bricks a little bit better, and we're going to do that in a fast and dirty way, not really be bothered with the accuracy or control, but I just want to show you that it's really fast in Grasshopper to visualize things. And we're going to do that only for the right side of our pavilion, or for the right side of our wall, because the components we're going to use and the workflow is the same for the right side and the left side. If we're done, you can copy the set of components we used and basically deconnect and reconnect the first component, so it will also compute for the left side. So let's get started. There are different ways how to get the exact extruding length for our bricks from the curvature. We're going to use a method where we're going to project our rectangles on top of our surface, and according to how much a rectangle is deformed, we're going to base our extrusion length based upon that data. So we're going to use a component that's called project to BREP for that. So let's insert that component. It's simply called project. Not this one, because this one projects an object onto a plane, but this one onto a BREP or a surface. Now this requires us to insert three inputs. One is our curves, which is going to be our rectangles. The second one is going to be our BREP, which is going to be our surface. But let's first insert the third one, which is going to be the projection direction, which is going to be the x direction. So let's insert a unit vector, a unit x. And now let's insert our surface. Now this component takes around 5 to 6 seconds to calculate, if I'm not mistaken. Nice. So now we have all our rectangles projected. And let me zoom in a little bit to show you why we did that and how we can extract how much we need to extrude our bricks in the end. If you see that where the surface doesn't curve that much, you see that the deformity between the original rectangle and our projected rectangle is almost none. But if you go a little bit to where the surface bulges out, let's say, you see that there's a lot of difference between our original rectangle and the rectangle we projected, which means that on these spots we need to have a brick that's longer. So the way we're going to measure that is to measure the distance from the 4 corner points to the 4 corner points from the projected rectangle. We're going to do that using a component called discontinuity, the one we used in the beginning to get the center of our rectangles. So this will get our 4 corner points. Let's copy and paste it because we also want it for our projected rectangle. Nice. So now let's get the distance between all those 4. So let me also draw a line component so it's a little bit more clear. So now as you can see, so those are the distances from our original rectangle towards the projected rectangles. And you see that where the surface bulges out, the lines are longer. And if you go to a spot where the surface is more or less flat, you see that the lines are almost zero. Nice. Let me turn off the line component and also our discontinuity components. So we have 4 distances, but in the end we only want 1 distance per rectangle. So let's sort this list. And let's get the largest value, which is the most critical value, with a list item. And don't forget to reverse this one, because now we're getting the shortest distance, but we need the longest one. Nice. So now we have all our distances, and we're going to remap these values to a domain we set. So we have a little bit more control. So let's type in remap numbers. This is a really helpful component that I'm using a lot. We're also going to use it in the next lessons. It will remap a certain set of values to a domain you specify. So in the V goes the original values. The S is the domain of those values. And there's a nice component called bounds, which will get the the domain from all those values, don't forget to flatten the input. So as you can see, the shortest line was almost 0, and the longest line is .42. Now the t, that's going to be the domain we specify. So let's insert a domain component. Construct domain. And let's insert 2 sliders. Let's say we want to have bricks that go from 0.5 in length to 1 meter. And let's connect our domain to our t. Nice, so now if we have remapped our numbers, our last step is to extrude our rectangles. So there's 2 ways we can go about this. We can extrude our rectangles half of this value to one side and the other half to the other side. So the rectangle stays in the middle. But that means we have to join our bricks in the end. So what I rather have is that we move our rectangle with half the amount to one side and then extrude it with the full amount to the other side. So we keep one brick in the end. So let's insert a move component. And we need to move them on the x-axis. Now let's move them with an expression. So we need to move them half of the size in the minus direction, which is going to be our original rectangles, which is here. Nice. And now we extrude that moved rectangle with our full amount in the positive x direction. Nice. Turn off these. Nice, and as you can see, our rectangles are still in the middle, so that's nice. Let me zoom out a little bit. So it's already starting to get shape. It's a pretty nice shape. The only thing we need to do is to get the checkerboard pattern. That's our last thing we're going to do in this lesson. And we're going to use a very dirty way to achieve this. Later on, I'm going to actually be more preoccupied with the data structure. But just for visualization, we don't care about these things. So let's shift our branches one back. And don't forget to simplify this output. So by shifting one back, we lose a certain organization, but for now that's fine. We're going to use the dispatch component. And the pattern is already set to true false, which resembles more or less a checkerboard pattern, which is nice. So what I'm going to do now is I'm going to flip the list, because if you take a look at our output, we have the A and our B, which are already more or less organized in a checkerboard pattern. We just need to organize them also in the other direction. That's why I'm flipping the list. And also for the B direction. And I'm going to insert 2 more dispatch components, and I'm going to connect them both to our flip list component. And now if I insert a B-rep and connect it here to the A, which is going to be one side of the checkerboard, and the bottom one to the B. And that's it. So now we have nicely our checkerboard pattern. Let me turn off the left side, so it's a little bit more clear to see. So basically, for visualization purposes, we're done. We don't have to do nothing more. The issue is that we have a lot of different types and sizes of bricks. I think there are around 800 bricks right now, and they all have different sizes and lengths. So it's quite likely that you would have to rationalize and standardize these bricks. And that is exactly what we're going to do in the next lessons. And also, although we have control over our domain, we still don't really know the exact size until we need to extrude the brick. So it touches exactly the other brick, let's say. So we know the exact size a brick needs to have. And that's also what I'm going to show you in the next lesson, that there's another component that will allow us to have more control over the exact extrusion length. And when we know the exact extrusion length from a brick, we can also determine more precise and standardize the final outcome of our bricks, let's say. So thank you for watching, and I'll see you in the next lesson.